Quantum computing is a rapidly emerging technology that harnesses the laws of quantum mechanics to solve problems too complex for classical computers. Today, IBM Quantum makes real quantum hardware, a tool scientists only began to imagine 3 decades ago, available to hundreds of thousands of developers. Our engineers deliver ever more powerful superconducting quantum processors at regular intervals, alongside crucial advances in software and quantum classical orchestration. This work drives toward the quantum computing speed and capacity necessary to change the world. These machines are very different from the classical computers that have been around for more than half a century. Why do we need quantum computers? For some problems, supercomputers aren't that super. When scientists and engineers encounter difficult problems, they turn to supercomputers. These are very large classical computers, often with thousands of classical CPU and GPU cores. However, even supercomputers struggle to solve certain kinds of problems. If a supercomputer gets stumped, that's probably because the big classical machine was asked to solve a problem with a high degree of complexity. When classical computers fail, it's often due to complexity. Complex problems are problems with lots of variables interacting in complicated ways. Modeling the behavior of individual atoms in a molecule is a complex problem because of all the different electrons interacting with one another. Sorting out the ideal routes for a few hundred tankers in a global shipping network is complex too. Why quantum computers are faster? Let's look at an example that shows how quantum computers can succeed where classical computers fail. A supercomputer might be great at difficult tasks like sorting through a big database of protein sequences, but it will struggle to see the subtle patterns in that data that determine how those proteins behave. Proteins are long strings of amino acids that become useful biological machines when they fold into complex shapes. Figuring out how proteins will fold is a problem with important implications for biology and medicine. A classical supercomputer might try to fold a protein with brute force, leveraging its many processors to check every possible way of bending the chemical chain before arriving at an answer. As the protein sequences get longer and more complex, the supercomputer stalls. A chain of 100 amino acids could theoretically fold in any one of many trillions of ways. No computer has the working memory to handle all the possible combinations of individual folds. Quantum algorithms take a new approach to these sorts of complex problems, creating multi-dimensional spaces where the patterns linking individual data points emerge. In the case of a protein folding problem, that pattern might be the combination of folds requiring the least energy to produce. That combination of folds is the solution to the problem. Classical computers cannot create these computational spaces, so they cannot find these patterns. In the case of proteins, there are already early quantum algorithms that can find folding patterns in entirely new, more efficient ways, without the laborious checking procedures of classical computers. As quantum hardware scales and these algorithms advance, they could tackle protein folding problems too complex for any supercomputer. How do quantum computers work? Quantum computers are elegant machines, smaller and requiring less energy than supercomputers. An IBM quantum processor is a wafer not much bigger than the one found in a laptop. And a quantum hardware system is about the size of a car, made up mostly of cooling systems to keep the superconducting processor at its ultracold operational temperature. A classical processor uses bits to perform its operations. A quantum computer uses qubits, CUE bits, to run multi-dimensional quantum algorithms, superfluids. Your desktop computer likely uses a fan to get cold enough to work. Our quantum processors need to be very cold, about 1/100th of a degree above absolute zero. To achieve this, we use supercooled superfluids to create superconductors. Superconductors. At those ultra-low temperatures, certain materials in our processors exhibit another important quantum mechanical effect. Electrons move through them without resistance. This makes them as superconductors. When electrons pass through superconductors, they match up, forming Cooper pairs. These pairs can carry a charge across barriers, or insulators, through a process known as quantum tunneling. Two superconductors placed on either side of an insulator form a Josephson junction. Control. Our quantum computers use Josephson junctions as superconducting qubits. By firing microwave photons at these qubits, we can control their behavior and get them to hold, change, and read out individual units of quantum information. Superposition. A qubit itself isn't very useful, but it can perform an important trick. placing the quantum information it holds into a state of superposition, which represents a combination of all possible configurations of the qubit. Groups of qubits in superposition can create complex, multidimensional computational spaces. Complex problems can be represented in new ways in these spaces. Entanglement. Entanglement is a quantum mechanical effect that correlates the behavior of two separate things. When two qubits are entangled, changes to one qubit directly impact the other. Quantum algorithms leverage those relationships to find solutions to complex problems.